All right, so free body diagrams, real simple, right? But super important. Free body diagram, it's just a picture that shows all the forces acting on an object. And we're not looking for something detailed. We're looking at, literally, it's very, very simple. It consists of a dot and some arrows. That's really all it is. You'll see them done different ways, but they're all done the same, just slightly differently. When I was taught to do it, I was taught that you draw it, you do it on like a Cartesian coordinate system, and where the zero, right, the origin is the center of mass of the object, right? Some places you'll see it, they do like a box, or they'll draw the object. So if it's like a ball, they'll have a ball, and you draw the forces acting on it that way. Most ways, usually with AP, they'll either give you like a box or something, right? Or essentially what they want is they want a dot, and that dot is the center of mass. And we're going to assume that all the forces acting on that object occur at the center of mass of the object. All right? We don't know what center of mass is yet, but essentially we're going to take that as to be, this is where all the forces acting on the object, right? So even if force is pushing on your arm, we're going to assume that the center of mass is right here in our chest, and that's where the force is going to act on it, okay? So it's almost like we're a blob that doesn't have tentacles, okay? So if we get rid of these things real quick, okay? It's really, really easy. So let's just say we have your book, right? We have your book, and I want to draw a free body diagram for your book, okay? Looking at your book, the simplest thing and the easiest thing you can always get, and no matter what, you can get it. And if you completely draw blank on everything else that comes to drawing a free body diagram, every object has weight, okay? And remember that weight always goes straight down. So we're going to draw an arrow that goes down. And we're going to call it, I'll call it F sub g. Sometimes I call it W equals mg. Sometimes I call it W. I try to do F sub g. Sometimes it doesn't work. It's like breaking a habit that I've had for 20 years. Okay? So that always goes straight down. Okay? Now, if we're talking about our book, there's then the normal force, which is supporting it, pushing it back up so it doesn't fall. Here's an important thing. Remember that it's perpendicular to the surface. Okay? And I didn't draw that quite well enough because I couldn't see it. I still can't see it. Okay? So we draw it perpendicular to the surface, and in this case that is straight up, and we call it F sub n. Sometimes we'll just call it n. All right? Now the really important thing here is that we have the directions correct. Right? So weight is straight down, normal force is straight up. But if the book is not moving, right, it's static, it's at rest on your table, okay, the two arrows need to be the same length. Okay? That is super, super, super important. That the arrows, the length of the arrows is proportional to the magnitude of the force. Okay? So in this case, if we make the weight this long and the book is at rest, the normal force has to be the same length, but in the opposite direction. Okay? You follow me? If you do something like this on the AP test and the normal force is smaller than the weight, they're not going to be ridiculous and be like, oh, it's 1/4 of an inch smaller. They're not going to do that. But if it's noticeably not the same length, they will take off points. Okay? So let's say now... It depends on what's happening, honestly. In this case, because the book is not moving, they're the same length. Henry? Essentially, yes. Yep. If it's a heavier object, the weight would be longer, right? With the normal force would then be the same length as the weight. Yep. Because they have to balance each other out so that it doesn't move. If the weight is larger than the normal force, that implies then that the object is falling. It's moving. Okay? So now let's say Kaylin takes a book and she slides it across the desk. Right. Okay? When we do that, we now introduce new forces. If she's sliding it to the right, we now have a force being applied to the right, and I'm going to call it F sub A, where A is an applied force. Right? Along the way, you might just call it F sub 1. If you have multiple applied force, you might call it F sub 1, you might call it F sub 2, things like that. Usually those specific named forces that we talked about, they get F sub g, F sub n, okay? If it's a non-specific force, like ropes pulling on things or you have multiple people pushing on things, you kind of have a little more leeway in terms of what you call it. Does that make sense? Okay? Now, she's applying a force, but there's also friction on the book, all right? In this case, friction is going to go in the direction that is opposite the motion. Now, this is where it gets a little, not sticky, but in a problem, they would give you a little more information. Let's assume she's pushing it, and she's pushing it faster, 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 right? So the book is accelerating, okay? What our free body diagram would then show is that the force of friction would be smaller than the force applied, okay? And we show that by making the length of our arrow smaller. And we'll call that F sub F. And now, what kind of friction would it be if the book is moving? Kinetic. So I'm going to call it F sub F K. F sub K. Okay? So that we know that it's kinetic friction. Now, if she was pushing on the book and the book was moving at a constant speed, I'm sorry, let's say the book was not moving at all. So we'll just say Caitlin's really weak and she can't move the book. Okay? We're going to have F sub G. We'll have F sub N. We'll have the applied force. And then because it's not moving, the frictional force is the same length as the applied, and it's friction and it's static friction. Okay? So this tells us then that all the forces, the force pairs, well, it can't be pairs, I'm sorry, but the forces cancel each other out. Okay? And now, looking at this, we can tell that either the book is not moving or it's moving at constant velocity. We don't know which one it is, right? Just by looking at the free body diagram. We need more information. What's really important with this is when you do a free body diagram, it is only the forces acting, okay? Do not draw speeds on this. Do not draw accelerations on this. Do not put anything else on here except for forces. Okay? Does that make sense? Pretty simple, right? It seems simple. People find ways. Okay? Now, before we move it, so far these forces are perpendicular to each other. Before we move on to forces that are not perpendicular, Dan?
If the object is moving at a constant velocity, it would still be of static friction or be kinetic. If it's moving at constant velocity, it's still kinetic. So you can use that to determine if it's static or static.
Yeah, you could find that way. So now, couple things that the AP testing scores are going to look for. And you're going to laugh and you're like, what the heck? Go with me. You draw a free body diagram. This is acceptable, right? You don't have to write this down. Just put it in the back of your head. This would be acceptable as a free body diagram for an object just hanging out on a table or whatever, right? Not acceptable. This is not acceptable because you're not showing that the forces are acting on the center of gravity of an object. Okay? I know you know, but they would not accept this. Okay? This is where things get weird. Actually, let me draw it. They think this is okay. They think this is okay because you're showing that the final direction is in that way. Okay? I guess a couple years ago it was a huge fight about it.
Why would you even do it that way anyway?
I don't know why. It's just that's what they came to. So what you would do is, again, you're just looking at, all right, they're the same length, right? So they're equal, right? They're opposite. And because the final direction the arrow is pointing in is in the correct direction, we're going to say it's okay. Where this, to me, seems like it's more correct than this. I don't know why. I mean, clearly I'm not an AP reader, but that's what they went with. There was a big fight about it, I guess, a couple of years ago. So, ladies and gentlemen, draw all your free body diagrams like this, right? Make sure they're connected and make sure they're just straight lines. Okay? It is what it is, and it's kind of crazy. Okay? So now, another thing. Shh. Last thing we'll talk about today. Let's say we have a box, and we're pulling on the box with a chain at an angle. Okay? So imagine we're pulling on a box with a chain. Okay? And I want to know, what is the free body diagram of this? Okay? So I do it the same exact way I always did. I've got the center of mass of my box. I've got the weight. I've got the normal force. Okay? Now, you see the angle at which the force is being applied. It's pulling at an angle, right? So I'm going to draw it at that angle, exactly how you see it. Okay? And I'm going to call it T. Actually, I'm not going to call it T. I'm going to call it F sub T, right? T meaning tension, all right? Because we're using a rope or a chain, something like that, right? So typically if you rope, chain, string, tension. And then we have our, let's call it frictional force, okay? Sometimes it has to do just with the location of the pen. That's why it's not directly on there. Yep. No. Nope. Now, when, and this is a little bit towards when we get a little bit closer to the, next week, AP diagram, AP test, this is what they want for a free body diagram. Okay? If you have forces at an angle, they need to be, you just show the force. Okay? No, this would be it. Done. This would be a free body diagram. You'd get all of the points allotted for, like, probably 1 point. That's what they would give you. Colin? Yes, right. Clearly, if it shows that it's at a shallower angle, you just draw it at a shallower angle. Okay? Now, when it comes to solving a problem, this is the start. Okay? Remember, for us, we need to, when we have in forces a vector, if we're going to deal with these things, we need to look at them in terms of their components. And force has components. Okay? So when we solve a problem, AP test, this is what you draw. Part B may be then find out what this force is. Okay, and we'll get into that. But what you're going to need to be able to have in order to solve the problem is you're going to need the components of this angle, all right, of this force. So you're going to have to draw that on the free body diagram. And you would call this F sub Tx, so the x component of the tension, and you would have F sub Ty as the y component of the tension. Okay? So on a free body diagram on the test, no components. Okay? On the free body diagram on the test, no components. All right? And because of that, I'll hit you on the test if you have to draw a free body diagram and you put components on there. But when it comes to solving a problem that may involve one of these forces, the components are what matter, not the force itself. Okay? And what I usually do is I put a squiggle through it so I know that I'm not dealing with that anymore. Okay? These two represent this guy. Okay? Henry?
So, when you're taking the test, and you draw your free body diagram, and you have that angle at 15. Now, you go to solve the problem, you want to represent
The components?
draw a separate one.
Yeah, draw a separate free body diagram.
Just not in that part.
Yes. Yeah, if they ask for a free body diagram, you draw it without the components, leave it. Part B, draw another free body diagram, put the components in. Okay? Yeah, Brianna. Nope. Nope. No, I just put it on the side usually so that you can see it, right? You know, technically it should be right on top, but then I find you lose it.
Like if it was over, like,
So if we drew it like this instead,
no, like from the end of SFDS.
it's got to be from the center of mass. Okay. when I was taught, I always drew Cartesian coordinate system, right? And then I would have like, if this was my normal force, I would put the y component over here, so it wasn't on, so you could see them. They like it like this, so it doesn't matter as long as you show that it's coming from the center of mass and the direction it should be going in. Okay. I'm sorry? Yeah, I guess. But again, you're not going to throw these in here. You know what I mean? So